嗯，
3年。
美国不，英国、澳洲是3年啊。嗯，美国的话要5年、6年吧，因为他们有上课。第一年不是你要先上课，PhD 有上课，美国的 PhD 要上课第一年，像 Master 一样，然后而且他们那边要办公的，要帮忙教书，
那别的地方
去做研究哦，就读新的东西哦，读 paper。
最好是强，
你可能每个星期去见老师哦，讨论哦。
这样这样上课样
嗯，
是
没有在上课啊，所以为什么我的班会来叫你们一直问问题啊什么的，就是要 prepare 你们进这种班。呀，不是那种教书这样教书给你听，是吧？没有这样的东西啊，你要自己想啊。所以你刚才为什么讲去找新的东西，就是要这样，你觉得要自己读、自己想、自己讲也啊。哦，是这样的，所以没有人告诉你要做什么，没有人告诉你要做什么，所以就是说，所以我的班就是说，我不会再想告诉你做，因为啊，等你到了那个 master 啊、PhD 的阶段啊，没有人告诉你要做，就算有了，之后也没有了，你肯定会到一个 step 是没有人要跟你做，跟你生活一模一样。你可以假设有一天啊，可能你们有父母嘛，可能假设你父母在，我不是在做了，你假设你父母，对啊，独立啊，独立啊。我可能你还没有真正的体会意义上的独立啊，你可能听到学校老师跟你讲，哦，要独立，要独立，独立。那个独立是真的是不一样的独立，就是没有人告诉你，哎，今天要早上起来刷牙，吃饭了吗？没有人，已经没有了。那你这个时间要不要吃饭？这个时间要不要睡觉呢？全部是你自己选择的。你这样讲哈，这东西很重要，很重要，重要。至少啊，在我们这个课堂上啊，东西还是有答案的。但是哦，你到了那个阶段，你是没有答案的，你是没有答案的。
有对错的，
所以哦，很好啊，这是另外一个课题要讨论哦。什么叫做对错？为什么一个东西会对，为什么会错？然后你就可以想，为什么我们要制定道德？那是一个另外一个课题。啊，为什么我们要有道德？为什么道德讲的对的东西是对？哎，我跟你讲啊，我没有道德，不是我讲，我的是非题可以拿分。你要说我，因为我somehow懂这个世界的人要什么东西，可是他要的东西是我要的吗？我不知道，是我懂别人要的。这题我全对了，是全错。你先错。我一看他的是非题，我感觉真实啊，我就知道你要这个东西。好的，现在小学的时候，你们也是有的，在学的是非题。
英语耶，
是啊，
这可不用读了，
这样就
你只要有一个正确的观念。
对对对对对对，是这个意思，是这个意思，是这个意思，是这个意思。 Hello, 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 hello.
其实那个
Hello, 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 hello.
完蛋，
Hello. Hello, hello. Hello. No mic, 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 no mic. Hello, no mic. Hello, hello, hello. No mic, no mic, no mic, no mic, no mic, no mic. Hello, 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 hello. No mic. No mic. 说说又没有麦啊，说说。Hello，没有麦啊。Hello， hello， hello，no mic。不知道他会不会来？
Hello.
哎，Hello， there's no mic here. Mic doesn't work.
OK， 好的。
Okay. Finally. 哎，说说啊，这东西讲 work 啊，到底？你按一次那边就 call 了还是怎样
亮红灯，
？OK，
拿去跑来，
它就 talk back。可是我每次要按很多次它才 talk back，什么情况？
通常亮了就是接通，
这样我要讲话吗？我按了，我要不要讲话？
一个例，
不是，他听得到吗？问题是
他为什么？
没有，他要接电话了，他才可以听到我讲话，还是我一按我就可以讲了，然后他就听得到。他接电话，OK，
英语自备。
外面还是里面？
这是8点后。
哦，好，就等他来。
是谁？
啊，
这是谁？
等技术人员。
可以讲。
Okay. All right. Let's start first. The technician will come in a moment. So, what have we learned throughout the semester? We've gone through logic, a bit of set theory, then construction of natural numbers, real numbers, and then sequences. Right. So the most important thing in that chapter is the Cauchy sequence. Yeah, because Cauchy sequence are convergent sequence, but Cauchy sequence might have limit not in the set. And for example, we can take Cauchy sequence of rational numbers that converges to irrational numbers. So that's another way we can build real numbers. Our real numbers are rational numbers and irrational. And then after that, we introduce limit of sequence, and then limit of function. And then if we talk about limit of function, then we can talk about continuity. Then we can talk about the function is continuous. And then after that, we did differentiation. Then we did differentiation.
购买是下课是可以用，
可以，
可以的。
昨天还可以用。
跟但是我 check 过是问题
哦，
啊，是
卖坏了还是？
如果你是昨天可以用，
对，
应该不是坏啊。如果是这个新的话，我现在 check 不到，因为要上课，所以我们要等你们有空。
OK，
我现在不能用，
哦，
不然的话你们就要换课时。
其他卖接不到。其他麦可以用，有没有其他麦可以穿？
没有，因为如果是新的问题的话，你换一下麦也是一样的。
是啊，可是不知道是不是那么些问题。
400个，如果你的麦没有问题的话，就问题了。
我怕我的麦有问题，
你昨天也是用，
我昨天有用，但是它这几个礼拜有时候连得到测试，有时候连不到。
让我抓，我要回去拿。
OK，哎，我可以分享一下刚才我运用了数学说服了你做一件事情。可以啊，单就单，单就单，用啥？怎么用数学来分享一下？我就刚刚发文嘛。刚才他 try 了那个机器嘛，他说我的麦接不到。他说如果是机器坏，如果是机器坏，他现在不能帮我修，他要等下课过后才可以过来看这个机器，然后可能我可以换麦。然后我跟他讲，要不要换一个麦来用？但是他讲，如果是机器坏的话，换麦也没有用。然后他就先问我，这样你麦有没有问题 ？OK， 你前片有没有用？他用前片来，之前有没有用这个麦有没有问题？我跟他讲，昨天用没有问题，然后他就讲， 哦，我 suggest 你要不要用另外一支麦来 test 一下？他讲不用，因为如果机器坏的话，不用 test 嘛。所以我要讲convince 他去拿麦。我要convince 他的是麦要有。那我就讲了一句话，这几个礼拜我的麦有时候接得到，接不到。所以这样的话，它机器坏的 assumption 跟麦没有问题的 assumption，其中一个有问题哦，麦就有问题哦。这样就可以 test 麦了。哎啊，明白吗？你要破掉人家的那个 assumption， 然后你就可以。这是谁用错哦？要不然你就整天被人忽悠吧，被人忽悠，人家把你推来推去，推来推去，你就被人家推来推去，对。不要被忽悠，真的不要被忽悠。还有一次哦，你们不是 complain 吗？厦门大学，你叫那个人做东西，他叫你抛弃另外一个东西，对，抛弃另外一个东西。我那天就遇到这个问题啊，我去问一个我的 admin，他给我一个名单，他讲没有，你去找另外一个 admin 拿。OK 好，我去找另外一个 admin 拿。你知道那个 admin 讲过吗？我没有找回去你之前那个 admin 拿，我靠，封那个 loop 了，叫我要去找谁 ？OK， 所以我怎么讲呢？我讲没有，是你讲的那个 admin 叫我来跟你打。OK，stop 了。他讲 OK， 让我去问一下那个 admin。后来谁给我的这个名单？你觉得？第二个 admin 给我，所以他不知道他自己的是不是属于他的东西，或者他不知道从哪里来的。OK， 所以你学好数学，不要被忽悠了。OK， 不要被忽悠。所以每次我在班问你们，决定一下这个是对的是错的，决定一下这是对的是错的啊，所以你才不会被人家忽悠。OK， 因为我们数学我们知道什么对什么错嘛，所以我们可以 check 你，看一下你的想法对还是错。OK， 在现实生活中很难哦，不知道什么对什么错，所以用逻辑。OK 吗？ Yeah. Okay, so let's start. So the last thing we talk about is differentiation. Differentiation is a special limit we look at. We look at limit of secant function. Why differentiation is good? If a function is differentiable, then it is continuous. Okay, so if you know a function is differentiable, then it is continuous. And then there are a few properties from differentiability. So you have what do you have? You have Rolle's theorems, means values theorems, Cauchy's mean values theorem, and then you can prove L'Hopital rule yesterday. Okay, and then the other things for derivative is you can find the local extrema for your function. You know where is the maximum point, where is the minimum point. And so far, this is the use of derivative. And next, this is the second last topic for this course, is about integration. Yeah, integration. After integration, the last topic is about sequence of functions. Previously, you look at sequence of numbers, real numbers. Later, you look at sequence of functions. So before that, we will look at this integration. So what does integration do? We want to find the area under the graph. But graph might not be always straight. If you have a constant graph, okay, what's the area under the graph? Constant graph. Width, height, length, which is the rectangle. So you only know how to compute the area of a rectangle because this is formula. Width, height, length. Okay. But what's the width of this? What's the length of this area? Okay, maybe you might take this as your length. Okay, but sorry, this width as your width, right? But how about length? Do you take this side or that side? Or any length in between these two lengths? Take every length. Take every length. Take every length. Testing. Okay. Yeah. Okay. Okay. Thank you. Thank you. Thank you. Testing. Okay. Okay. See, the result is good using wax. The mic finally work. Why he bring one mic here and then this mic work? The resonance. Resonate. I don't know. Just now he touched his mic, right? And then touched my mic. But just if only touch my mic won't work. Don't know. Okay? Yeah. So it's good to make people bring one mic. Okay. So what length you should took? You see, the left length should be much shorter than the right length. Okay. So if you take the shorter length, right? What's the area? What's the length and width you get? You will probably just get this part here. Okay. And then what do you miss out? You miss out all the area above. Okay. But if you take the right length, then you overcount the area. Or you overcount the area. You overcount the area by the top part. So what should you do? What should you do? What should you do? You should attach smaller rectangle to this area under the curve. Okay. So you should attach smaller rectangle. Okay. What do I mean by smaller rectangle here? What do I mean by smaller rectangle? Rectangle with small width. Okay, rectangle with small width. So let's say we subdivide this width into this many. Okay. And then I can consider rectangle like this, for example. To fill up, okay, to fill up the area under this graph. Fill up the area under this. Okay. Fill out the area under the graph. Okay. So you can see that if I do this, the area that I miss out, right, is getting less than the previous rectangle. Okay. Maybe I include the previous rectangle like this. Okay. So I better approximate my area under the graph. So what can you imagine? If I subdivide the width more, I can get even better approximation under the graph. Okay. So what does this subdivision call? What does this subdivision call? Sorry. So we first define a partition of a closed interval AB is a finite set. Okay. P such that you have S0, X1, X2, to Sn. So you see, this is a bit like sequence, a bit like sequence, but we stop at finite n. Okay. such that what? Such that the first S0 should be your left endpoint of your interval. And then subsequently, x0 is less than x1, x1 is less than x2, and so on until you reach Sn. What is Sn here? Sn is exactly your right endpoint. Okay. So I give you an example. Let's say, can you give me partitions of 2, 5, for example? So you should imagine the closed interval 2, 5. Can you give me a partition of 2, 5 or not? Maybe Zheng Tan. 2, 3, 4, 5. Okay, good. So 2, 3, 4, 5 works. 2, 3, 4, 5. In particular, I can pick the easiest one. Okay. P0 to be 2, 5. Also can. Okay. And how about Xiao Tong? Give another partition of 2, 5. Two, 3, 5. Okay, yeah, sure, works. 2, 3, 5. Okay. Let me call another one, but I changed the question a bit. So let's do this. Right, Yixing, is P3 a partition of 2, 5? Why not? Because 6 and 7 is greater than 5. Good, very good. So this is the defining property of these S0 to Sn. Okay, they have to be less than 5. Good, very good. Okay, so this is not a partition. Of 2, 5. Good, very good. Okay. Right. So next, so we will define what is upper sum and lower sum. So we'll define the rectangle in particular that we see yesterday. So consider a function f from a, b to r, and consider a partition of your domain. Okay. Partition of your domain. So let's write out our partition as S0, comma x1, Seng, AB. So we will define what is upper sum. And we will define what is the lower sum. Okay, let's give you the algebraic form first, and then we will talk about the picture, how you should imagine this picture. So let's do upper sum first. So we'll define upper sum of f and p. Okay. So when I write like this, right, what does it mean? UFP. This U is depend on the function I gave, is depend on the partition I make. Okay. So this is a sum of what? So this is a sum of 1 up to n of mi times xi minus xi minus 1. Okay. So when I write like this, right, what's the thing that you know already? The thing you know is xi, because this is the partition. So you should imagine just now, let's say AB is 2 and 5. So you fix one partition, right? So there's 1, 2, 3, 5. There's 1, 2, 2, 4, 2, 2, 3, 4, 5. Okay. And then what is MI here? Okay, so MI here is very important. So where MI is the sup of
fx for x in the region xi minus 1 to xi. Okay. So you see, before you look at this mi, right? If you look at this definition here, Si is partition, but there's nothing about function yet. So the function part have to come into the definition of mi. So this mi is depending on fx. So what does this sentence mean? Supremum of fx where x is in this interval. What does this mean? Now what does this mean? What does this mean? Okay, let's look at this example. Copy, paste. Okay. So let's say what? Smaller a bit. Okay. So let's remove what we have drawn here. Okay, let's do less work. So let's reduce a bit. So let's name this S0, and then this one S what? Let's say we do only S3. Okay, so let's say we put X1 here, X2 here. Okay. So let's look at this function with this what? This upper sum. Okay, function. So you see, I fix a function. Okay, and then I fix a partition. Okay, let's see what does this upper sum do. Okay, let's see what does this upper sum do. So how many mi in this case? In this example, how many mi? How many mi? Yeah, you have n equals to what? 0, 3. Yeah, n equals to 3. Okay, good. So let us draw this here. Okay. So what is, let's say, what is M1? Okay, where is M1 here? Okay, where do you find M1? So you look at all the points. So let me write down. So you look at the supremum of fx such that x is in S0 and x1. So where is this point here? Where's M1? So you look at all the x in between x0 and x1, and then you look at the fx, and then find the maximum. Where's the maximum here? Where's the maximum? Somewhere around x1 here. So somewhere around x1 here. So should be somewhere here. Should be somewhere around here. So this is M1. Okay, M1 here. Okay. M2 eh? About M2. S1, right? So at M2, it is exactly happen at X1 here. So quite close. Let me move this a little bit. Okay, maybe I draw like this. Here is M2. How about M3? M3 happen at S3. Is everyone following? Okay. So, but what do I mean by I multiply M1 with this interval here? This means what? M1 becomes my length. Xi minus Si minus 1 become my width. Okay. So you can see that what am I doing in the upper sum here is exactly the rectangle business here. So let's draw the rectangle out. So M1 times S0, sorry, X1 minus S0 is the area under this rectangle. And then M2 multiply X2 minus X1 is the rectangle, is the area under the second rectangle. And then the area under the third rectangle is M3 times X3 minus X2. Does everyone follow? Following? Okay. So you can see how we call this an upper sum. So what does upper sum do? It overestimates our area under the curve or the graph. Okay. Overestimate. Does it make sense? Because I take the maximum fx. I take the maximum. So maximum meaning there might be someone less than you. Okay, within the region xi minus 1 and xi. Okay. Or there might be someone less than you. So you overestimate that part. Okay. So since we have this overestimating object, we can also do some underestimating rectangle. So we will define this as a lower sum. Okay. So we define L lower sum as L FP, okay, that is equals to the sum of I to N of little mi. Okay, we call it little mi of xi minus xi minus 1. What do you think I should define this little mi to be? We define it to be the infimum, okay, the smallest one, infimum of fx such that x is in xi minus 1 to xi. Okay, infimum. Okay, so in this case here, let's see where's the infimum. Where's the infimum for M1? Little M1. So we can see that little M1 is here. Okay, the infimum is here. Little M1. Where's the little M2? Okay, little M2 maybe around here. All right. Okay, and then little M3 is in the happen at the X2. Okay, does it make sense? Okay, you can see what happened is the real area under the graph happened between these two sum of rectangle. Correct or not? It happened in between. So if you imagine, I made the upper sum closer to the lower sum, then they will eventually equal to the area under the graph. Okay. Can you imagine or not? Imagine first, then later I will make precise to you. Can you imagine? If you cannot, you need to ask. Okay. So how do you imagine? You make your partition smaller and smaller. Okay? And then you can see that the upper sum and the lower sum can converge. If you make your partition smaller and smaller. Can you imagine or not? Yes. Yeah, say. Yes.
Lower sum is taking the value from x1, xn minus 1. But from what you shown, the lower sum is taking the lowest value.
Correct. And then what was the difference? Let me say just now.
What I use, what I use the sum is I take value of x0, then I take value of x1.
Okay. Yeah. Okay, that one is Riemann integral actually. That one is Riemann integral. You just take arbitrary fx inside your integral. So about this topic, later we will mention it in lecture also, and I will also make it into a tutorial question. Okay, what if you don't pick supremum or infimum? You just simply pick any f in the middle of xi and xi minus 1 or xi plus 1. If you pick any fx in between this domain, okay. Can you also get this kind of integrability problem solved? That is the Riemann integral. So this particular construction is called the Darboux integral. So we take this upper sum and lower sum business. So we consider the sup or consider the infimum. Okay. Make sense? Does it make sense? Okay. Okay. So from now on, you should imagine. You should start imagining already because we deal with n infinity, right? So you should start imagining if I partition more, okay, if I get more partition in, so maybe S0, S1, S2, S3, S4, F5, X6, okay. And then similarly I consider the upper sum and lower sum. Okay, you should see that the two rectangles should getting closer and closer to each other. Okay. Closer and closer to each other. All right. So from this picture, what can you see? We can see that the rectangle is always higher or taller than the blue rectangle. So how do we make this statement precise here? So the proposition here is for every partition P of AB, LFP is always less than or equal to UFP. UFP. So how to prove this? Okay, the proof is very straightforward. So you just start from the left-hand side and then go to the right-hand side. So let's start with the definition of LFP. So let's test. So what is the definition of LFP? Going to refer back. What's LFP? What's LFP? Here. What's LFP? So, what did you say? What's LFP? Sum of what? Sum of what? Sum of little mi times the difference between xi minus 1. But what is little mi here? Is the infimum, okay, infimum of fx such that x is in xi minus 1 to xi, okay. So LFP is defined to be the infimum of fx that x is in xi minus 1 to xi. Multiply with the width. What's your width here? Xi minus xi minus 1. Okay. So this part, you can think of it as your length, the little mi is the length, and then the xi minus 1 is your width. Okay. So then, how do you relate to UFP? UFP, the difference of UFP is the length becomes sup. So inf is greater or sup is greater? Sup, oh, correct or not? So the inf of fx should be less than or equal to the sup of fx. Make sense? Okay. Then you still keep your width, is the same width, because we are using the same partition. So in the end, you get UFP. Okay, so very simple. Yes, question? Oh, sorry. Yeah, should go too many. So why when because my index become n, so I finish this. Okay. Okay. Any question or question? No. Okay. So far, okay. Okay, good. So just now we talked about we want to subdivide more. Okay. So what's that process? We will define it as a refinement. Okay. So if we start with a partition, let's say p equals to s naught dot to xn, okay, of AB. Then a partition of Q, or I say call it Q, of AB is called a refinement of P. If P is in Q. Okay. So what does it mean by P is in Q? That is, if Q equals to, let's say, y0, y1 to ym, then xi equals to yj. So for some j in 0, 1, to m, and for every I in 0, 1 up to n. Okay. So how should you understand this? How should you understand this? So for example, let's say, for example, we will say that, say, 2, 2, 3, 5 is a refinement of 2, 5. Okay. So 2, 3, 5 is a refinement of 2, 5. Why? You can find 2 inside 2, 3, 5. You can find 5 inside 2, 3, 5. So in this case, we will say that this 2, 5, since 2, 5 is a subset of the set containing 2, 3, and 5. Okay or not? Okay. So there's a concept playing around here. You think that refinement gets smaller, right? Okay, but somehow it's a bigger set. Anyone think of it like this? When you get refined, right, isn't that you get smaller? But the definitions seems to suggest that this refinement is a greater set, a larger set. So you need to think about this. Okay, you need to think about this. What does refinement really means? Okay. Any question about this refinement? Okay, it's like subdivision. Okay, subdivide. Any question about this? Any question about this definition here? Refinement? No? Okay. So let's discuss about one proposition and then we will break first and then before we proving it. So so this proposition will say that refinements really refine. So what does it refine? So consider a function from AB to R and partition P equals to x naught, x1, xn of AB. Okay. If Q is a refinement of P, then we can see that the lower sum of P will be less than or equals to the lower sum of Q, and the lower sum of Q definitely less than or equals to the upper sum of Q, and upper sum of Q is less than upper sum of P. Okay. Okay, so this is what we are trying to convey last time. If you make your partition smaller, then the lower sum will increase and the upper sum will decrease. Should we draw some picture? Let's draw some picture. Let's get some picture here. The similar graph again. Okay, so let's say we have a S0, X1, and X2. Okay, so where's the upper sum and lower sum here? Upper sum will look something like this. Yeah. Okay, so this is M2. How about M1? M1 should look something like this. Right. Okay, so this is the upper sum. How about the lower sum? Little M1 should go somewhere here. And little M2 should go below. Okay, so this is, let's say this is P. Okay, so P is S0, X1, and X2. Okay, let's say we define Q. How do we define Q? Okay, let's say we have S0. Sorry, let's use the different one. Y0, Y1, Y2, Y3, and Y4, for example. Okay, such that what? Such that Y0 equals to X0, Y2 equals to X1, and Y4 equals to X2. So what am I doing here? What am I doing here? So here, X0, I make it Y0. X1, I make it Y2. Okay, Y2. Yes, Y2. And then Y2, I make it Y4. So where is the Y1 and Y3? Where should Y1, Y3 be? By definition. So Y1 have to be in the middle of Y0 and Y2. And then Y3 have to be in the middle of Y2 and Y3. So which one to pick? Doesn't matter. I just fix it first myself. Okay, I fix it here. I fix it as a middle one for now. Okay, this is my definition. So Y1, Y3. Okay. So in this case, how many M do I have for Q? 4. Oh, 4M, huh? So I have four rectangle for upper sum. I have 4 rectangle for lower sum. Okay. So for upper sum, what do I get? Should I use a different color now? What if I use this color? Can everyone see or not? Not very visible. This color. Nobody. Let's see, use what color? Maybe use red one. Okay, so Y1 here. Y1 maybe is here, Y1. Y2, I guess similar. M2. How about M3? M3, the size get reduced down, maybe here. Okay. So maybe let me draw it like this. M3. How about M4? M4 go up a bit again. Okay. All right, so this is the upper sum for Q. How about lower sum for Q? Lower sum for Q. What color should we use now? Let's use purple, try it. So lower sum for Q, okay, not very visible. How about lower sum for Q? Should we do now? How about use green again? So lower sum for Q is like this. And lower sum for M2 is somewhere here. And then lower sum for M3 is similar. But something changes, right? Lower sum for M4 is a bit more than the previous lower sum for P. So what's the difference here? Where's the difference here? So let's mark some difference. So between so let's look at the so what is the difference? So let's look at what's the difference between LFP and LFQ. Okay, so let's compare the orange and the green part, the green rectangle. So the difference here is the white part here. So you can see that when you make more subdivision, okay, or we call it refinement, if you refine your partition, your lower sum increases. Okay. How about upper sum? How about upper sum? So let's compare LFQ and LFP. Okay, let's compare these two. So what's color of LFQ? Color for LFQ should be purple, pink. LFP, UFP. So UFP, the color of UFP should be blue. Okay, so let's compare purple and blue. Okay, so blue with the pink. Okay, so where's the difference? Okay, so difference happens in M3. Okay, so the difference here is the blue rectangle has extra white bit than the pink. Make sense? Everyone follow? Any question? Question? No? Okay, so in general, how we prove it, we will left to next hour. Let's take a break and then we'll see how we prove this theorem. So let's wait until 10:08. Oh. One thing.
Yeah.
我要是
这关系
能用
没有什么那个 drum 上面一个东西。
哦，是天的作品。
呀，
我们的那个内容是介绍那个数学家，再介绍那个
介绍那个数学家为什么他出这个名？当然，你在介绍这个过程，一定要跟别人聊天。
这个数学家，
这两个不错，
你不要把整个故事你不要把整个
八个人
介绍出来，
介绍出来，
不要讲你的出身啊，在哪里啊，
这个不用
这哪里要做什么，
不太重要，你就只是介绍一下他做什么东西。对，
就是你要为什么要的主题去介绍。
在书面上画的那种。
对，不要太仔细，不要跟我讲他在哪一个里面。
哪个真健身
所以
这个应该也会写吧？是啊，
好多听看。有一个期限是谁给的？是，可是我没有给过这个期限。
懂了，就我问的时候，
你的呀，
然后我听到的都会自己设。
自己选择，然后我这
那个 drum 是说，我需要我们玩有声音吧？对啊。刚才玩的比你对啊。
没有，
我就这样，两人会叫。要第一笔来做。
很丢。
回去了，
哪个是有？我现在我删了，
这森林的房子，
你知道？哪张？
会在手臂找，也是拿电脑，有对着电啊，
我是
有爱是手
有啊？什么？
这里分水在好，
啊？
有苹果，
什么？像我 iPhone 手机，
有 iPhone 手，
我有。
我的地方分手，
听不懂。
分手，
安分手机。
哦，你的 iPhone
我的 iPhone 手机，在这里，
哎，后来周杰伦要买了，哎，卖完了没？他们会再加。
我买
叫
加条？几时？那你有报纸出来没？
我看过，
没有看到新闻呢。
内幕消息今晚宣布加长10月了
10月27号，
还问题多一点，
多一天。
26、27
不知道啊，就是有人发消息出来可能会加长。
星期六还是？
抽烟，
他在讲今晚呢。
哦。
烟。
的确，来可以给到钱的，我已经按 A 了，那 J expect 要跳出来叫我入盒，
对啊，
那我那边有钱，
上不去也得买吃。
对啊， 我就觉得哎，不是那个，
哎，他那个1000块这样子做的，
怎么做？都这全部都99，全部都有位置，就是不要扣钱，位置不要放。
我是讲，如果要去的话，不要坐前面，不要坐在一起。
我电话可以放大。
像我在家里看人家有这么
终于让你现在
如果你这样子的话，我觉得你 focus 可以放在，哎，你 focus 可以放在那个 root 的那个 point 的东西 ，and then 怎样到后来出到这个 rose 的
哪一个是真
theorem and then 它是用这个 rose theorem 去解回那个 root 的东西。
大概
我上面一个有生
还是它只是一个赛区感？
你们加油！快要4点了，
然后这个
OK 咯，这个是你的 main thing 要 present 咯。它是把 rose 用在这里的。Yeah，then 那你就不用 pro 什么 rose 你要 focus 是怎样把 rose 用在这边，
才100块。
所以这个是他本人要用处理上。OK， yeah，
就是之前我们因为我什么的。是被给关系差不多个死。
OK，
都做了就给OK。专说那个4种被大家就说那个他就做了这个也是这也是这个比分因为你看的话是2种
可能整个东西你看下去的，像整个东西讲完，或者可以有些能够不用知道，只要知道说会有，它可以把东西变成光的底蕴。
好的，然后只有的话专去一次都给钱的，是吧？
因为有些就是有些太仔细的，所以我们比较有用的是说，我来讲啊，假设他有一个题目要解。我不知道他讲心理，但是我不大 care， 因为我现在还不知道我是几月的话，我想要知道是如果他有一个题目要解，那先跟你讲，他已经过了那前礼拜了这个题目，但是题目somehow equivalent to loss，而这一个 equivalent 要讲清楚，在一次过多少，那才算。如果你觉得这个 equivalent 很短，可以somehow再塞一点，他讲前礼拜 ，OK， 你再塞，可以给到，把 main thing 是说这个 rose 的人讲 equivalent 是我们要守的那个。
当然有些只有这
个是最重要的，
课程还是有些可以同班起来只有更便宜。
当然，可能现场会有人问你，为什么？可能你讲的很好，然后人家还是会问你，为什么可以被 simplify 的？好的，你也要知道一点这样子的，就是说不是我的意思就是说，不是说你不要去读啊。只是说你不能都不用选择去present，可以跟到我讲吗？现在蛮多东西的，所以说重点的话，就是那你对不对？你要设计出这样的线，后面的再说。因为如果你一开始给我们这样多东西 simplification 东西我们没有 motivation 去看。
我其他东西我就
而且对 analysis 也没有用啊，因为它是好像 algebra 的题目，
Yeah.
如果你不差钱，
不上我。
把你的 M 进去那个点里面，然后用 Teams 这边
你看反对呢，我是顺便
啊，也可以，如果你有这个观点，也可以提出来，也可以提出来。比如说 game theory 的 invention 不是为了 economics，那个人是要 solve pure math 的问题。那 somehow 这 game theory 是为了 economics，然后他就拿到 Nobel Prize。
我就用。
Hello, testing. Okay, let's start. Shall we start? Okay, you see, this proposition, this kind of proposition is relatively, how to say, straightforward to prove. Why? There's very few conditions here. What's the condition you really have? There's only one condition, really. You have a refinement of P, that's all. And then 你就要搞出这么多花出来。There's only refinement of P. Refinement of P, yes. Okay, Q. And then you can deduce this LFP less than or equals to LFQ. Less than or equal to LFQ, UFQ, and then U less than or equal to UFP. But out of these three inequality, some of them should be easy to see, right? From what we know. Which inequality is easy to see? Out of three of these. Three inequality here. 1, 2, 3. Yeah, out of these three, which one is easier to see from what we know? The middle one, right? UFQ, LFQ is less than or equal to UFQ. This is what we have proved because we proved for random partition just now. Okay, so what is not clear is LFP is less than or equal to LFQ and UFQ is less than or equal to UFP. So what is not clear is the other two. So instead, we will just prove. We will just prove LFP less than or equal to LFQ. Okay. And then the other one, the proof of UFQ less than or equals to UFP is similar. Okay, similar. And it will be left as exercise. Okay, similar. Okay, so let's focus on proving LFP less than or equal to LFQ. So what do we do? First, we start with the partition we have. Okay, S0, X1 up to Xn. And a refinement of Q. Okay, a refinement of P, which we call Q. So let's call it Y0, Y1, to Yn. Okay. So when we say Q is a refinement of P, right, what does it mean? P is a subset of Q. So you can think of it like P is a subsequence of Q. It's not quite a sequence because N is not infinity. But you can think of it as a sub-terms inside Q. Okay, so in this case here, since Q is a refinement P, we have an increasing function, increasing function J from 0 to N to 0 to M, such that EI equals to SJI for each I in 0 2. Okay. Can everyone understand this increasing function? What does this increasing function do? Everyone understand? Okay, I think I saw some blur face. Wait, let me do an example for you. So for example, let's say we have P here, we have Q here, right? So let's say what do we have for P? And what do we have for Q? So let's say we have P S0, X1, X2 is enough. Let's say S0 is 2, S1 is 3, S2 is 5. Okay. And then Q, we have more stuff because it's a refinement. So let's say we have Y0, Y1, Y2, Y3, Y4, for example. And what do we have for this term here? Let's say we have 2, 2.5, 3, 4, and 5. Okay, so where's the increasing function here? I can send x0 to y0, x1 to y2, x2 to y4. Okay, does it make sense? Okay, okay, so this is the increasing function we have. Okay. No question? No question? No? Okay. Cannot decrease, you cannot go bottom. Okay, so this is not allowed. Okay, good. Right, so this is the increasing function. Then what? Okay, so this is our business coming in now. So we want to show that LFP is less than or equals to LFQ. So we start from left-hand side first, LFP. So what's the definition of LFP again? Let me ask. Roland, what's the definition of LFP? Sum of what? Times X I minus and 1. So I summing from where to where? No, I mean I, the index I, summing from where to where? 1 to where? Depend on my labeling here. So my P is going from 1 to N. Okay. Not starting from 0, you know why? Because 0 appear in the first term here. Okay. Okay, good. So this is our definition. All right. But what is this M1 here? So M1 is the infimum of fx. X is in xi minus 1, xi of xi minus xi minus 1. Okay. All right. So this is a LFP. So, I mean, how do you relate? Okay, let me draw this picture here. Okay, let's draw a picture here for this particular case here. So if you want to prove, so one technique in proving pure max statement, you need to be able to see the proof in a particular example. Okay, so let's look at this particular example, 2, 3, 5. Okay, and the refinement 2, 2.5, 3, 4, and 5. Okay, how can you relate the partition P to partition Q? Okay, how do you relate these two? How do you relate these two? Sorry? Say again. Substitute. Sequence. Can you elaborate more? Elaborate more. What do you mean by sequence? It's not quite a sequence because sequence got infinitely many terms. But here, stop at some end. Okay. So how do you relate these two here? When I say I want to relate, meaning let's say how do you view 3 minus 2 and 5 minus 3, for example? Can you also get 3 minus 2 in the refinement or not? Can or not? Can you get 3 minus 2 in the refinement? What happened to this pink part and the blue part in the refinement? It also get refined, okay, get refined. So it get divided. So the pink part become 2 pink part, and then the blue part become 2 blue part. Okay. So what can you see here? What can you see here? Actually, 3 minus 2 equals to what? 3 minus 2.5 plus 2.5 minus 2. Can everyone see it? Can see or not? Can see it? This 1 pink part become 2 pink part. Okay, so 3 minus 2 become 3 minus 2.5 plus 2.5 minus 2. Make sense? Okay. So what can you write here? Okay, what can you write here? So I can rewrite the sum here. So I equals to I from 1 to n of infimum of xi. So my job here is I want to rewrite the difference of xi minus 1 using the refinement. Okay, using the refinement. So let's see how I do this. So I'll make this a sum from let's say, will I confuse you or not? I hope not. So let's do this. So j of k minus 1 plus 1 up to jk. Wait. Okay. Can everyone understand this notation here? What is this notation here? Let me see. Will I confuse you? Okay. 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 I think I confused you a bit. So let me change this sign to k. Okay. Does this make sense now? Let me think. Let's see. Wait. Let me think. This is making sense. So j. Okay. Let's see. Let's check together whether this makes sense or not. If I k equals to 1, what is this? This is j0 plus 1. What is j0 plus 1? J0 should be 0. Okay. So because x0 gets sent to y0. And let's see. I think we don't want this. Say. And what is J1? J1 is where you send your x1 to. Correct? So this green, this blue, this pink part here is your J. Then you send 0 to 0, 1 to 2, and then 2 to 4. So 0 here is J0, and then 2 here is J1, and then 4 here is J2. Okay. Does it make sense? So, yeah. Correct. This notation here. Everyone following? Is everyone following? No question about this notation? Say again. Why? Should we cover everything? Y1 is not covered. Yes, Y1 is not covered by J. But when you sum this out, right, where are you summing? So JK minus Y is J0. So you start from 0. Oh, correct. So I need a +1 here. Correct. Okay, so I mean, let's be concrete, right? Let's be concrete. So let's be concrete. We want to be really concrete here. So when K equals to 1, what happens really? So this sums here is summing from I equals to J0 plus 1 to J1. Okay. In our example, what are we doing here? What are we doing here? So what is J1? What is J0 in our case? In this example here, what is J1 and J0? What is J0? J0 is 0. Okay. Can you follow? And this part here becomes J equals to +1. What is J1? Where is J1? J1 is where? J1 is 2. Okay, J1 is 2. Okay, J1 is 2. And then summing from Yi minus Yi minus 1. But what is this sum here? Zheng Kan, did you get your Y1 or not? Let's see. So how do you sum here? Sum two terms here. What are the two terms here? The first term is Y1 minus Y0. The second term is Y2 minus Y1. Okay. But in our case, what is Y1? What is Y0? What is Y2? What is Y1? 2.5 minus 2. And then Y2 is 3 minus 2.5. See? This is covering the first. So this is covering what? Y1 minus Y0. Yeah, which is what? Which is 3 minus 2. Okay, can everyone follow? Can follow now? So this is how we describe the process of breaking the pink part and breaking the blue part using the refinement. Okay or not? A question? So the hard part is how to understand this notation here. Okay, so to understand this notation here, you need to plug in the right index. Okay or not? So question? Yes, of course, that's why we put an equal sign here. Yes, so, yeah, what we really do is this thing here. 3 minus 2 equals to 3 minus 2.5 plus 2.5 minus 2. Yeah, it's the same. Yes, exactly the same. Okay, we describe the previous width using the refinement width. Correct or not? Okay, we describe the width, the previous width using the refinement width. Make sense? Does it make sense or not? Does it make sense? Okay, okay. Okay, good. So what's the next thing we can do? The next thing we can do is we can throw the finite sum to the front. Okay, we can throw the finite sum to the front. Okay, we can throw the finite sum to the front. Okay, we can throw the finite sum to the front. Okay. Does it clear why we can throw the finite sum to the front? When we fix a k, this is really a constant. Okay, so we can multiply every constant into here. Okay, does it make sense? So when you fix a k, this increment is a constant. Okay, so I can multiply into every term here. how should I put this? So this is like, so let me do some analysis here. What is doing in this step here? So it's like m times a sum of n of yi I minus 1. What do? I can first multiply every term with m. Okay, so this is what I did to pull the sum outside. Make sense, everyone? Okay. No question? No? Okay. Okay. So this is how I pull the sum out. Okay, using this part here. For each k, it is a fixed m. Okay, for each k, it is a fixed m. So why do I do this? Why do I do this? Why do I do this here? Why do I do this? Because what I can do is I want to replace, okay? I want to replace the choice of my infimum of fx using the refinement now. Okay, I want to do it now. Okay, how do I do this? So my claim is this is less than or equals to the sum of k equals to 1 to n, and then the same sum you have here is, and then this is less than equal to the what? Let me remove this guy. Infimum of fx of x in yi, yk, okay, minus wait, let me think. Yeah, minus k minus 1. Hey, why am I writing in my notes? Okay, pretty stupid. Right? So this of yi minus yj minus 1. Okay, let's check. Is this correct or not? Okay, I think this is wrong. So I should make this I. Okay. So what am I doing here? Let's do an example. Let's do an example. What time is it? Okay, I still have time. So let's do an example here. So let's say I have y0, y3 here, and then y2 here. Okay. And then I consider the lower sum. Like this. Then lower sum at y2 minus y3 is like this. Okay. And then I introduce refinement. Let's say y, so let's use different color. y0, y1, y2, y3, and y4, for example. Okay. So what do I do? How do I go from the refinement? So I mean, how do I go from the lower sum of p? Lower sum of p. Let's write down what's our p here. X0, x1, and x2. Okay. I don't know how to count, so let's correct it. And go to the refinement of p, which is q. Let's say y0, y1, y2, y3, and y4. Okay. How do I do this proof? First step, I split the width x1 minus x2 into what? y2 minus y1 minus y0. And this is the first thing I do just now. Okay. I split it into this part here. Then I split it into this part. But what did I say? I move the sum up. What does it mean by that? I move the sum up means what? I consider the infimum of the previous. So the infimum from the p. multiply with the new width. Okay, so this is what I did in this step here. So let me make a note here. So in this step, what do I do? Okay, I multiply the previous height with the new width. I multiply the height with the new width. Okay, did you change anything or not in this case? You not yet, right? Not yet changed. What you do is you subdivide your previous lower sum. That's all. And finally, this case here, this case here is special already. So this case here, let me use another color. So this case. How about this case? I replace the height now. Okay, how do I replace this height? The increment here I taken from y minus 1 to yi is no longer si minus 1 and si. So meaning what? My height can go higher. Okay or not? So in the yellow part, the height I consider is the increment between yi's. Okay, so you see, for the first increment is the same, but for the second increment is different already. Oh, you see? Can see or not? Okay, how about the third increment? Third increment is around the same. How about the fourth increment? Fourth increment increase. Can see? Can everyone see? So you see, so the purple expression and the yellow expression, what's the difference? The difference is how we pick the if. Okay, the first if we take between xi. The second if we pick within different yi. Okay, if I pick within yi, you can see that at certain yi, the increment is taller than the increment we get from the whole xi minus 1 to xi. Does it make sense? Question? Oh, question. I think here we need a question. Any question? Does everyone get what's the difference between the purple part and the yellow part? What's the yellow part and purple part doing? Question? 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 Can follow? Question? Before understanding this notation, you need to understand what I want to do first. And then you can check whether this notation is doing what we are trying to say. Question? Question? Any question?
The upper line.
Okay.
The interval.
Why?
The interval is the index of interval is high, but we still pick the height, the interval based on the interval
Of xi.
Of xi.
Yes.
Which is on index k.
Yes, that's right.
Move the second line.
Yes. There's no more k. Yes. Okay. Why the sigma k is still there? Because the sum inside this sigma k, right, is the sum within this part only. It's the sum within this part. Okay, let me draw it to you. Count big and count small. No, the index k is counting this. Okay, when k equals to 1, it is going from S0 to x1. When k equals to 2, it's going from x2 to s1 to s2, and so on. Within the x1, s2, you count everything at every subdivision inside. Okay. Yeah. Can follow the idea? Only then you check the index is correct or not. Okay. Any more? Got other question? A question? Feel free to ask. Don't say. Don't think that you are stupid. No one is stupid. The stupidest person in this world is the person who don't listen. Who don't want to communicate with people. Okay. This is the stupidest person in this world. Okay. If you don't know, you are not stupid because baby don't know anything. So you are baby. You are baby in mathematics. It's okay. Everyone follow? The purple line and the yellow line. Purple line, yellow line. The sum, what the sum is doing. Is it clearer or not? Is it clearer? Okay. If it is good, then what do we do next? Then I can combine the two sum. Okay. Instead of count part by part, I just count everything. Okay. How do I count everything? I just replace the whole summation by I, by a single I. Okay. I just return to my usual definition of lower sum. Okay, and then here is multiplied by yi minus 5 minus 1, which is equal to LF cubed. Okay. No question? Any question about this proof here? So the first step is you have lower sum, the orange one, and then you subdivide using the new refinement. And then if you look at each refinement, let's say the purple one, the purple circle here, you can see that if I consider a different increment, okay, around this refinement, the lower sum increases. Okay, so this is the less than or equal part. This is the yellow part. Okay, you can see that the yellow part is greater than the purple part. Okay. Greater or equal to. Okay. Maybe it doesn't increase, but it might increase. Okay. When you make smaller partition. Why it should increase? Why should it increase? Why increment increase? Maybe from the picture it's easy to see why increase, but from abstract point of view, so my point is here. So actually there's a lemma here. If A is a subset of B, then the infimum of A, how do you compare the infimum of A and B? Smaller than equal to, let me think. I think yes, smaller than equal. Wait. B might have more things, right? B maybe have smaller thing. Okay, so greater or equal to. So is this apply here or not? Does this apply here? You see, xk minus 1 to sk has more things, right? But yi minus 1 to yi has less thing. Okay, so the infimum of less thing is greater or equal to the infimum of more things. Can see? Correct or not? Okay. So I mean, this is the proof that we should know how to prove from the supremum infimum case. Do you know how to prove this? Will contradiction be easier? Let me think. How? Suppose inf A is smaller than inf B, and then where's the contradiction? Not clear to me. Not clear to me how to do that.
Yeah, right.
Because we are yeah, sure.
Somehow, if A is on my contradiction less than if B, then there must be a number in A that is smaller than the number in B. But all the numbers in A is in B.
Okay, I mean, oh yeah, okay, use that point first. So since Since I think something is obvious here, so let's prove this and then we will finish this class. So since A is in B, means what? So every lower bound for B is a lower bound for A. Correct or not? So since A is in B, is as a subset of B, every lower bound of B is an lower bound of lower bound. So what does this say, sir? For every lower bound M for B, for every A in A is less than equal to. Then what can we do?
It's also a normal and thus is a normal.
So in particular, A is less than equal to if B or A. Alright. Why? Cannot in particular, right? I mean, this particular is why particular.
Then since
Because
it's
if there is
any
elections,
Sorry. Okay, who want to go first?
so since A is also bounded below, right? So if A also exists,
Correct.
and if B is also lower bound, so from definition of greatest lower bound, we must have if A is greater than or equal to infinity.
Okay, so I mean, A is bounded below by if B. So if A exists, and then
Since if A is the greatest lower bound, and if B is
one of the lower bound.
the lower bound of A,
Okay.
then if A must be greater than or equal to if B.
Okay, makes sense. Well, so this in particular correct or not? This in particular.
this one is correct.
Every lower bound.
But in particular,
Where,
if A is a part of this small.
Wait, no, not yet. I mean, this part is correct or not? Can we resume to this part? Why is this true? If B is a lower bound of B. Ah, okay. Okay, true. Okay, good. So, okay, so let's start again. So since A is in B, again, it's a subset of B, then every lower bound of B is a lower bound of A. Okay. In particular, if B is one of the lower bound for B. So it is a lower bound for A. Okay. Now what? Now, since A is bounded below by what? If B, okay, then what? Then if A is what? In A is a lower bound of A, and actually it is the greatest lower bound of A. Correct or not? So inf B is the lower bound for A, but inf A is the greatest one. So inf A have to be greater or equal to inf B. Okay? Clear now? Okay. Of course, this discussion is about whether, this discussion is built on the existence of inf A and inf B. If inf B doesn't exist, then nothing to say. If inf A doesn't exist, nothing to say. Okay. So if they happen to exist together, then this is their relationship. Okay. But one intuitive way to think about this is if your B is larger, strictly larger than your set A, it might contain more things, right? More things, the things inside there could be less. Okay, this is the intuitive idea. But how to prove it, you need to use the definition of infimum. Okay, similarly, you can draw similar argument for supremum, and then you will use that argument to prove the upper sum of FQ is less than or equal to the upper sum of FP. Does it make sense? Okay, so that's why I catch you very hard during the supremum, infimum sequence and limit, because you see what we build on derivative, we build on integral is really the limit and supremum, infimum stuff. Okay or not? Okay. So you see this lemma here, we go back to first few weeks. Okay, any question before we break? Any question you want to ask? Question? And so today, what did you learn? You learn about the Darboux integral, okay, the Darboux sum, or the Darboux upper sum and lower sum. And then you learn about refinements, okay, and then how do you relate upper sum, lower sum of refinements to the original partitions? Okay, how do they compare? And then this inequality here is very, 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 very important. Okay, later when we're gonna prove integrability. Okay, so you can see that after you do refinement, right, the upper sum and lower sum somehow get closer to each other. So can you imagine there's one midterm question, right? A1, B1, A2, B2, A3, B3, A4, B4, that thing. Remember? Yeah, this is what we are creating, the sequence here. If you add in more refinement, for example, R, S, T, U, V, W, X, okay, you can see that you can form this kind of sequence. Okay, squeezing. Okay, squeeze. Okay, any question before we break? Okay, if not, we'll see you next week.